Guess it was a little cold out.
Okay. Okay, we'll go ahead and get started. Can the people on Zoom see my screen and hear me?
Yep.
Thank you. So today what we're going to do is we're going to review the exam 2 answers. And then I've posted the answers on Canvas. So if you want to take a look at it later, you can. Then we'll start chapter 6. And before we do that, though, there's a couple announcements I want to make. One is that lab this week will not be in the normal room. It will not be in the 4th floor laboratory area. It'll be in EAB 110. So the other thing about that is, since that's a computer lab, it can hold up to 12 people. And so we won't be having the shifts in lab. So far this semester, we would have half the students come in for the first half of the lab time, and then the second half of the lab time would be another shift of students. So for this lab and then the next 2, those will all be computer-based labs in EAB 110, and so there's no shifts. Everyone should show up at the beginning of lab time. And it'll take more than an hour and a half to do the labs, so you'll need all that time. So please come at the start of the lab. None of this shift stuff where half come and then half come the second half. So once again, that's EAB 110. So if you had me for lab, I gave you the wrong room last week. Hold on. If you had me for lab, I gave you the wrong room. It's not it's not on the second floor of the science building. It's in EAB 110. So, okay, the other thing is we're going to move up the quiz for chapter 5 to Wednesday. So it was going to be next Monday. I've decided to move it up to this Wednesday so that we don't get too far away from that material. It'll be almost 2 weeks since we finished wrapping up chapter 5, but since we got done with that a little bit early, this Wednesday will be the quiz on chapter 5. So today we'll review exam 2. We'll start chapter 6. On Wednesday, we'll continue with chapter 6 for the first part of the class. And then the second part of the class will be a quiz on chapter 5. This is going to cause a little bit of a change in the course schedule for the next few weeks. So I will post that on Canvas so you can take a look at that if you'd like and see what's coming up. Any questions about either the lab room change or the moving up of the quiz to Wednesday, the chapter 5 quiz to Wednesday? Okay, then I'll start going through the exam. So the first question, how many mils of 10 molar NaOH would you need to use to make 1 liter of 0.01 molar NaOH? So this question is very similar to what you had to do in the lab, where you had to determine how many mils of your solution you needed to pipette in order to make a more dilute solution. So this is using that M1V1 equals M2V2 formula approach, where M1 is the concentration of the more concentrated solution. V1 is the volume of that you would need to use. And then M2 is the concentration of the solution you're trying to make, and then the volume of that solution. So if you set up M1 V1 equals M2 V2 and then solve for V1, you would get 0.001 liter. And that would then be converted into mils because the question asks for how many milliliters and the answer is 1 mil. So I have to tell you that a lot of people miss this question. I was kind of surprised by that because we had talked about this using this M1 V1, M2 V2 approach in class. You also had done it in the lab. There's some things that you learn in Gen Chem that you may or may not ever use again. This is one that if you stay in any type of science, you're going to use all the time. Knowing how to dilute a more concentrated solution to make a more dilute solution is a pretty common thing to do. So if you weren't clear on how to do this, please take a look at it and make sure that going forward you understand how to apply this, because it is a skill if you stay in any type of physical science that you will need to have. Okay, questions 2 and 3 centered around using those rules, the tables around solubility. So in number 2, when aqueous solutions of which two are mixed are precipitate forms. And the answer is sodium chloride and sodium nitrate. And what you form is you form a solid silver chloride. In 3, which of the following will the ammonium ion form an insoluble salt? Well, the ammonium salts are all soluble. So the answer was none of the choices. They all are soluble. Number 4 asks you to write the net ionic equation for the reaction between aqueous nitric acid and aqueous sodium hydroxide. If you think back to when we talked about this, writing these equations, we said you could write a molecular equation, you could write an ionic equation, and then you could write a net ionic equation. So the ionic equation would be the molecular equation would be the second choice, the HNO3 plus NaOH going to NO3 plus H2O. So in those molecular equations, we keep all the compounds written as molecules, don't show any ionization or anything like that. Then the next thing you could do is you could write it as the ionic equation. And that's what I have written here, the H plus NO3 minus plus Na plus OH minus going to water plus Na plus NO3 minus. Remember, when we talk about writing the ionic equations, what we're talking about is for the compounds that are dissociated, we write those as their cation and anion. And once again, that's based on those solubility rules. And then if things are not dissociated, then we write them together. So that's the ionic equation written there. Then the net ionic equation would simply be looking to see which ions are exactly the same on the left-hand side, in other words, the reactant side, and the right-hand side, the product side. And in this case, you had NO3 minus on each side, and then the sodium Na plus ion on each side. If we go ahead and cancel those out, then that leaves us with our net ionic equation, which is H plus OH minus to give us water. Number 5, oxidation is the loss of electrons, and reduction is the gain of electrons. So oxidation, loss of electrons, reduction, gain of electrons. Number 6, which is a correct expression of molarity. So molarity is moles of solute per liters of solution. So it's not mils of solution, it's not liters of solvent, it's liters of solution. So moles of analyte of solute divided by liters of solution. Number 7, which solution contains the largest number of moles of chloride ions? So the information you were given here was mils of the solution, molar concentration, and then the molecular formula. And so the information we'd want to get out of this is we have a molarity, that's moles per liter. So if we're trying to calculate moles, we would have to change the mils into liters in order to cancel out the liters units and get it into moles. So that's where on the first one you see 0.01 times 0.5. So the 0.01 going from mils to liters, we move the decimal 3 places to the left. And so that 10 mils becomes 0.01 liters. We have a 2 there because in our molecular formula, we're told there's 2 moles of chlorine. So we use those subscripts in the molecular formula to tell us how many are in each of those compounds. So for BaCl2, there's 2, sodium chloride, there's 1, ferric chloride, there's 3. So in each case, we took our mils, converted it into liters, then we took the number of moles of each of those, so 2, 1, 3, and then times the molarity. And if you multiply those out, you see that the third one, the FeCl3 solution, has slightly larger number of moles of chloride than the others. Number 8, a strong electrolyte is one that ionizes completely in solution. One of the things you need to remember about electrolytes, we talked about one of the properties of electrolytes, strong electrolytes, is they're good conductors of electricity. To conduct electricity, you have to have ions present. And so if something just dissolves but doesn't ionize, then it doesn't conduct electricity. So the examples we talked about in class were something like salt, sodium chloride, that completely dissociates. Salt solutions are really good conductors of electricity. Something like sugar, which dissolves but doesn't ionize, is a poor conductor and actually doesn't conduct electricity. So here, the strong electrolyte, the key there is ionization, because you need ionization to conduct electricity. Number 9, which of the following are strong electrolytes? So once again, this gets down to, do things dissociate or not? So HCl is a strong acid that dissociates. Acetic acid is a weak acid, so it doesn't fully dissociate, so it's not a strong electrolyte. Ammonia is a weak base, so it doesn't totally dissociate either. And then KCl is a salt that we've talked about, and so that totally dissociates. So that once again, if it totally dissociates, it's a strong electrolyte. So HCl and KCl were the answers there. Okay, number 10, what are the spectator ions in the reaction between potassium chloride and silver nitrate? So this is kind of similar to the earlier problem where we needed to write, where we will need to write the molecular equation and then the ionic equation, and then finally the net ionic is what we're after. Because we want to see which of those ions are going to serve as spectator ions, and we can cancel out. So here I've written the ionic equation, potassium and chloride, both that dissociate, so you have potassium and chloride ions. Silver and nitrate that dissociate, so you have those ions. When we do this, we do that exchange of the cations or that metathesis reaction. And now the potassium goes with the nitrate, the silver goes with the chloride, and we think about our solubility tables in that to see if it dissociates or not. We know that potassium with nitrate dissociates, so we have potassium ions and nitrate ions. Silver and chloride, that precipitates out, so we have silver chloride as a solid. So we go, and I've circled the ones that are the same on the left hand, in other words, the reactant side, and which ions are the same on the right-hand side, the product side. And so we wind up with silver ion plus chloride ion gives us silver chloride precipitin. And so that tells us that the potassium, the K plus, and the nitrate, the NO3 minus, that those ions are the spectator ions. Number 11, what's the concentration in molarity of a sodium chloride solution prepared by dissolving 9.3 grams of sodium chloride in sufficient water to give 350 mils of solution? So we have grams of sodium chloride and we have a volume of solution, and we want to get to molarity. So since it's molarity, we know our end units need to be moles per liter. And so we can convert the 9.3 grams of sodium chloride to moles by using those atomic weights we were given to calculate the molecular weight for sodium chloride. That's the 58.5 value. And by having that in the denominator, we have grams of sodium chloride canceling grams of sodium chloride, and now we're in moles of sodium chloride. And then the denominator needs to be in liters. So 350 mils, if we convert that to liters, we move the decimal 3 places to the left to give us 0.350 liters. So if we divide those numbers and do the math, we get 0.45 molar sodium chloride. In 12, which is not a combination reaction, the key here is when we look at the last reaction, the methane plus oxygen to form CO2 and water, we said that a combustion reaction involves oxygen reacting with something to form CO2 and water. So that was the key to getting this one correct, is recognizing that CO2 and water were products associated with something that had oxygen as a reactant. Any questions so far in anything I've gone over? Okay, 13. Another one that refers back to some of those solubility guidelines that were in the table. Which of the following is soluble in water at 25C? In this case, the one that's soluble is the silver nitrate, the AgNO3. 14 was an oxidation number question. So remember what we talked about when we have things oxidizing and reducing in that, one of the things we're looking at is to see how this oxidation number, which is a bookkeeping type number, how that varies based on what the molecule is. And so we had some guidelines on this as well. And the way I approach this type of problem is there are certain ones that I'm a little more confident in that I'm gonna know what the oxidation number is, what it typically is. And I go ahead and determine those first. So for the first one, NaNO3, I know that oxygen is usually -2. And so there's 3 of those. So 3 times -2 gives me a total of -6. Sodium is always +1. And my molecule, my NaNO3 molecule, has no charge. So what that tells me is when I add up these individual oxidation numbers for sodium, nitrogen, and oxygen, it has to equal 0. So if I've got -6 total from the 3 oxygens and +1 from the sodium, -6 + 1 is -5. So that tells me that the nitrogen in this case has to be +5 as its oxidation number. When I look at HNO2, I'll do a similar thing. I know that oxygen is usually -2, so I'm going to call that -2. There's 2 of them. So that's 2 times -2 for a total of -4. Hydrogen is usually +1, so there's +1. So now I have a -4 and a +1. That leaves me with -3. So to balance that out, to get it to equal to 0, the nitrogen has to equal +3. So its oxidation number is +3. NO2-, this one's a little bit different because instead of adding things up to equal 0, the individual oxidation numbers of the elements need to add up to equal -1. So for oxygen, I'll start with that one again because that's usually -2. So 2 times -2 is -4. If I'm trying to get to -1, then that tells me the nitrogen oxidation number would need to be +3. And then finally, the last one, NH3. Hydrogen, I know, is usually +1, and I have 3 of them. So 3 times 1 is 3. So that means in this case, the nitrogen must be -3. So I go back and I look and I see the first nitrogen, it was +5. The second and third ones were +3, and the fourth one was -3. So it tells me the highest oxidation number is that +5 value that I got on the NaNO3 compound. Okay, 14. How many grams of phosphoric acid are in 155 mils of 3.50 molar phosphoric acid? And then you're given the atomic weights. So if I have a volume and I have a molarity, I know that I can use that information to change the volume into a mole value. If I get into moles, then I know I can use the molecular weight of the compound to convert moles into grams. So those are the relations I'm going to use in order to convert this volume of H3PO4 into grams of it. So molarity is moles per liter, and I'm given the volume in milliliters. So the first thing I need to do is convert the mils into liters. And I do that by simply moving the decimal 3 places to the left. And so that's 0.155 liters. Then I have 3.5 moles in the numerator, 1 liter in the denominator. So my liters units cancel. And now I've converted into moles of H3PO4. And then I use those atomic weights. So it'd be 3 times 1 for the hydrogen contribution, 1 times 31 for the phosphorus, and 4 times 16 for the oxygen. I add all those up and I get 98.03 grams of H3PO4 per mole. And so by putting the grams in the numerator, moles in the denominator, my moles will cancel out and I'll be units of grams H3PO4. So then if I do that math correctly, I get an answer of 53.2. So some of the keys there were you needed to remember to change your mils to liters. You also needed to get your dimensional analysis lined up correctly. So you had the right things in the numerator and right things in the denominator. You used molarity to convert from volume to moles, and then you used molecular weight to go from moles to grams. Okay, 15. Potassium chloride solution was prepared by dissolving 9.3 grams of KCl in sufficient water to give 350 mils of solution. What is the molar concentration of this solution? So once again, when I see molarity, I know I need to be in moles per liter. I have 9.3 grams of KCl, so I will use the molecular weight of KCl, which is 74.6, to convert that 9.3 grams into moles. And then since it's molarity, moles per liter, I need to take my 350 mils and convert that into liters. Once again, moving that decimal point 3 places to the left, it tells me that's 0.350 liters. So now I have moles divided by liters, and that answer is 0.36 molar. Okay, number 16 is a balancing equation problem. So we're told C8H18 plus O2 goes to CO2 plus water. So the first thing I did is I balanced the carbons. So I had 8 carbons on the left-hand side of the reaction. So by putting 8 in front of CO2, that's the only carbon source I have on the right-hand side. It balances the carbon out. Then the next thing I balanced was the hydrogens. Remember, we'll save those oxygens to the end. So if I look on the left-hand side, I have 18 hydrogens from the C8H18 compound. The only source of hydrogen on the right-hand side is the water. So, and there's 2 of those in the water molecule. So if I put a 9 in front of that, then I have 18 hydrogens there and I've balanced that out. So then the last thing to balance is the oxygens. If I add up the oxygens on the right-hand side, I have 2 times 8 is 16. And then I have 9 times 1 from the water is 9. So I have 25 oxygens on the right-hand side of the equation. Since my only source of oxygen on the left is the O2 molecule, it's 2 times whatever the coefficient is. So if I want to get 25 on the left, if I put 25 over 2, then 2 times that is 25. And so now everything balances if I go back and check. The problem is we don't want to have fractional coefficients in front of the molecules. So in order to get rid of that 25 over 2, I need to multiply each of the molecules by 2. And if I do that, then it becomes 2 C8H18 plus 25 O2 going to 16 CO2 and 18 H2O. So in this one, once I got it balanced by kind of going through the balancing process, I had an instance of where I did not have a whole number coefficients. So I had to do an extra step to get that into whole numbers. Okay, 17, calculate the percentage by mass of nitrogen in P2, Cl2, and H3, 2. And you're given the atomic weights of the various elements. So when we think about percentage mass of something like this, where we want to know the percentage mass of one of the atoms, or one of the elements rather, in the molecule, we talked about converting the amount of calculating the molecular weight for the whole thing, and then calculating the contribution to that molecular weight of the element that we're interested in. In this case, it's nitrogen that we're interested in, and we look at our molecular formula, and we see there's 2 nitrogens in there. So 2 times 14, that's the atomic weight of nitrogen, is in the numerator. Then the denominator is just our molecular weight. So for platinum, it's 1 times 195. Then we add 2 times 35.5 for the chlorines. Then 2 times 14, that's that nitrogen contribution. And then plus for the hydrogen, there's 3 hydrogens in the NH3, but there's also 2 of those NH3 ions in there. So we have 2 times 3, then times the atomic weight of hydrogen. So if we then have this ratio, we want to multiply it by 100 because we said we wanted a percentage. And by definition, percentage means you've multiplied it by 100. So if you do that math correctly, you get 9.33%. Okay, number 18. How many molecules of methane are in 48.2 grams of it? And then we're given the atomic weights of carbon and hydrogen. So whenever you see how many molecules or how many atoms, that should be a tip-off that you need to use Avogadro's number. And if you're using Avogadro's number, that should tell you to get to the Avogadro's number, you have to go through moles. That's that relationship of atoms or molecules per mole. So we see the molecule clue. That tells us Avogadro's number. If we're using Avogadro's number, we got to get things into moles. And then we see we're being told that we have 48.2 grams. So if we're starting with grams and then moving from there, we know we have to use the molecular weight of the compound to change that grams into moles. So 48.2 grams of methane, the molecular weight is 16.04. So if we have the 16 grams in the denominator, we see our units cancel there. Now we're in moles of methane. Then if we have Avogadro's number per mole, the moles cancel. So we have Avogadro's number in the numerator. And then if we do the math correctly, in other words, if we've practiced with our calculator, so we're comfortable using the scientific notation keys and the exponent keys, then we'll get 1.81 times 10 to the 24th molecules. Number 19 is another balancing equation problem. So there, I started out by balancing the aluminum first. And so 2 aluminum on the right, putting a 2 in front of aluminum nitrate on the left gives me 2 there. Then the next thing to balance for me was the sulfur. So if you had 3 sulfurs on the right-hand side, putting a 3 in for the N2S balances the sulfurs. And so then the only thing left to balance is the nitrogen and the oxygen. So what we see is if we look at the oxygen, we had 3 times 3 times 2 on the left. And so, and then to balance that, we put a 6 in front of the NaNO3 on the right, and then that balances that out. And fortunately, that the nitrogens balance out with that as well. So you could either done the nitrogens, looked at it as doing the nitrogens, or looked at it doing the oxygens. Either way, it would work out. So that left us with coefficients of 2, 3, 1, and 6. Okay, we have the combustion reaction of propane, and we're told that if 2.5 moles of oxygen are consumed, how many moles of CO2 are produced? So in this case, you needed to look at the stoichiometry of the reaction and then figure out what the correct mole ratio was that you wanted to use. So a big part of that is writing out your dimensional analysis correctly so that you have the right thing in the numerator and right number of moles in the denominator. So if we have 2.5 moles of O2 and we then go look at the reaction, we know that 5 moles of O2 will produce 3 moles of CO2. So since we're in moles of O2, the 5 moles of O2 needs to be in the denominator. So the moles of O2 units cancel. And then the 3 moles of CO2 need to be in the numerator. And that's the units that we want in our answer. So then if we do that math, we get 1.5 moles of CO2 are produced. Okay, 21. And this was probably the most involved question. So if you got it right, congratulations. There's a few things you had to do here to get it correct. We have this reaction of aluminum and oxygen to form aluminum oxide. And we're told that we have 5 grams of aluminum and 5 grams of O2 to start with. So what we needed to do is figure out which of these reagents is going to be the limiting reagent. So in other words, which one's going to run out first. And that will determine how much product we can make. And so the first thing to do is to change each of those gram amounts into moles. And so using the atomic weight of aluminum, we change that 5 grams of aluminum and see that it's 0.185 moles. And then we take the 5 grams of O2 using that molecular weight, that's where the 32 comes from, and change that into moles of O2. We then go and ratio those two. And we say that if moles of aluminum, which was 0.185, is divided by moles of oxygen, which is 0.156, that ratio is 1.19. If we go up to our balanced chemical equation that we were given, we're told 4 moles of aluminum react with 3 moles of oxygen. So if we put 4 over 3, that molar ratio, we see that that's 1.33. We compare the 1.33, which is what we need to have a stoichiometrically correct reaction. And we see that our experimental data, our weights that we were given, tell us that we only have a 1.19 ratio. So that means that the numerator is not big enough. The numerator, remember, was our moles of aluminum. So this is telling us, by comparing the weights we were given to the mole ratio of the reaction, that we don't have enough aluminum to react with all of that oxygen. So that tells me that the aluminum is the limiting reagent. So I can ignore that oxygen moles and focus on the aluminum. And so I took the 1.185 moles of aluminum, used the mole ratio now from my reaction of aluminum versus aluminum oxide. And we see there that's 4 moles of aluminum produces 2 moles of aluminum oxide. I have the 4 moles of aluminum in the denominator so that my moles of aluminum will cancel out. 2 moles of aluminum oxide in the numerator. So now I've switched that 0.185 moles of aluminum to moles of aluminum oxide. I can switch from moles of aluminum oxide to grams of aluminum oxide by using the molecular weight. So I would go ahead and calculate that out. That would be 2 times 27 plus 3 times 16 for a total of 102. And then I use that information to cancel out the moles of aluminum oxide units and wind up in grams of aluminum oxide. And that answer is 9.4. So in this reaction, where we were given 2 amounts of the starting materials, so the reactants, the first thing we needed to do was determine which of these reactants is going to run out first, which is going to be the limiting reagent. And just as we had the example in class about the hamburgers and buns and all that, whichever one is the least amount that you have that you need to make it go forward, that's going to determine how much you can ultimately make. And so in this case, by calculating out what those grams were, converting them into moles, because when we compare stuff in reactions and we look at stuff in reactions, we want to be looking at moles, not grams. And then using the stoichiometry of the reaction, we were able to determine which of those was the limiting reagent. Once you did that, then it was straightforward using mole ratios and converting from moles to grams to get the amount of material you were going to produce, the amount of aluminum oxide. Okay, 22, calculate the formula weight of zinc chlorate. And so there you were given the atomic weights of the different elements. And so it was a matter of, for zinc, 1 times its atomic weight, and then chloride 2 times its atomic weight. And then for oxygen, it was 2 times 4 times its atomic weight. And you add all those up and you get 264.3. Number 23, what's the empirical formula when you're given a compound with these mass percents? Well, what we wanted to do was convert each of them to moles. And so if you assume 100 gram total, then these percentages just become weights. So 66.6 divided by 12 to give us moles of carbon, 11.2 divided by 1 to give us moles of hydrogen, and 22.2 divided by 16 to give us moles of oxygen. So then you see you have 5.55 moles of carbon, 11.09 moles of hydrogen, 1.39 moles of oxygen. We're not finished there because we want whole numbers as our subscripts on the molecule when we write an empirical formula. And so the way we get there is by looking and seeing which mole value is the smallest. In this case, it's oxygen at 1.39 moles. And we divide that and then the other values by that lowest mole number. And if you do that, you get 4 moles of carbon, 8 hydrogen, and 1 oxygen. So our final formula is C4H8O. And then our last question, if theoretically a reaction could produce 4.79 times 10 to the 8th grams of water, but experimentally it produced 4.01 times 10 to the 8th grams of water, what's the percent yield of water for the reaction? So we talked about percent yield. That's a calculation where we take the experimental number that you get divided by the theoretical number. And then since it's a percentage, you multiply by 100. So in this case, if you took the 4.01 times 10 to the 8th, which was the experimental value, and divided it by 4.79 times 10 to the 8th, which is that theoretical number for grams of water produced, and then do that math and then times 100 to give a percent, you get 83.7. So that concludes the test. Does anyone have any questions about any of the questions on the exam? Okay. So overall, the class did pretty well, I think, on the exam. There were several students who got 100, so congratulations to those of you who did that. I think the class average was probably about 75, 76%. which is not bad at all, which is good. So that'll wrap up this test, and now we're going to go on to chapter 6. So let me close this off, and it'll take me a moment to pull up chapter 6. Okay, are you seeing the chapter 6 slide?
Yep.
Okay, thank you. All right, so rest of today and the next lecture or so, we'll be talking about chapter 6. And for me, this is where we start trying to put some of this stuff together. You know, sometimes they teach this section a little sooner in the chapter. But this is where we start looking at what's going on at the atomic scale. And we start learning about just the energy involved in things, in atoms and molecules. We'll do a lab on electronic structure of atoms, not this week, but the following week. And then the week after that, we'll do one on the molecules. So here's where you start to get into more of what I would call the chemistry stuff of it all. And so some of the stuff that we've talked about or done in labs, you'll start to see some of that show up here. So what we'll be talking about here is we'll be talking about how the electrons are associated with in the atom. And also we'll be talking about the energy associated with that. And what we'll see is when we're talking about energy, we're really most of the time talking about light. And the other thing we'll talk about is that light has dual properties. It has, and one of the properties is a wave type property. And so we'll be talking about that duality of light and what that means and how that explains some of the stuff we observe. So when we talk about waves, and you can see the little cartoon here, which kind of looks like a little, like maybe in the ocean or a lake or something. And that's really what we're talking about when we talk about light. It comes in these waves. And so when we talk about electromagnetic radiation, as I said, that's kind of a generic term for light. Doesn't matter the wavelength of the light or the frequency of the light. It's all electromagnetic radiation. And light moves, everyone's probably heard of the term speed of light. That's how fast light moves. Doesn't matter the wavelength, light moves at the speed of light by definition. And so, but when we talk about a wavelength, that's literally the length of the wave. And so in this kind of water cartoon on top, you see that from one crest to the other, that's the length of the wave. That's the term wavelength. And wavelength is designated by this symbol you see down at the bottom that looks kind of like an upside down Y. So that wavelength is the symbol that we use to tell us how long that length of the wave is. So in other words, how long the light is. The other thing that we talk about is something called frequency. And so that's the number of waves that pass during a specific amount of time. And the higher the frequency, the shorter the wavelength. And you see that on this labeled A and B. So on top, we see that's a longer wavelength, but there's only two of them there. There's only two apexes in that, two crests in the wave. In the bottom, we have 4. So the frequency is higher in B, because in each of these, we're assuming that that black line drawn across the middle is the same time scale. So let's assume that that is a second, that is the time scale. We see on top, we had 2 crests in that time frame. In the bottom, we have 4. We also see that the length of the wave in the top is bigger than the length of the wave in the bottom. So that's that relationship between wavelength and frequency. And a couple other things let's talk about just to reinforce this wavelength concept. So light doesn't have mass. Nothing's faster. That's why you hear someone say travel at the speed of light. That's really fast, right? Waves, as we'll see, light has both wave and particle properties, as we'll see. We're talking about the wave properties now. In a few moments, we'll talk about the particle or photon properties in a bit. So the photons we'll talk about a little bit, or think of those as little energy packets. So molecules and atoms like to have transitions based on specific energy packets interacting with them. And this gets to some of the things we'll talk about in a bit. The wave properties talk about the wave oscillating in terms of an electric and magnetic fields. So that wavelength symbol, that upside down Y, is actually the Greek letter lambda. And that wavelength determines the color of the light. And you think back to when we did some of the spectrophotometric labs with the colored dyes and things like that, the wavelength determined what color the dye was. And that wavelength also determines how much energy one of its photons carries. And so the energy of a photon associated with that is inversely proportional to the wavelength. So if the wavelength, as the wavelength gets bigger, so that denominator gets bigger, the energy goes down. If the wavelength is shorter, so in other words, the denominator gets smaller, the energy goes up. So energy is proportional to 1 over the wavelength. We talk about frequency, and frequency is this symbol looks kind of like a small V, but it's actually the Greek letter nu. A lot of times people just write V because they don't want to look up the new character in Word or something like that. But it looks like a little V. It's called nu in reality, but that's the symbol for frequency. And frequency is the number of cycles or the number of crests in that wave that you see at 1 point per second. So you'll see frequency expressed as seconds to the -1, 1 over S, or you'll see it expressed as Hz. Hz is hertz. And so if you're listening to the radio or something, they'll say the frequency that the radio is at, and it'll be some number of hertz. And so all of those are ways that people call frequency. 1 over S, S to the -1, or Hz for hertz. Any of those are acceptable ways to express frequency units. Just like energy, frequency is proportional to 1 over the wavelength. And so here we see that frequency equals c, which is the speed of light in meters per second, divided by wavelength. And if the speed of light's units are meters per second, then the wavelength has to be expressed in meters to make the units cancel out correctly. So what this tells us is, if we look here and we see that frequency equals c over wavelength, we said there that the energy of the photons associated with the light is equal to 1 over wavelength. That tells us that energy is directly proportional to frequency. So whereas frequency is proportional to 1 over wavelength, and energy is proportional to 1 over wavelength. Energy and frequency are directly proportional. Let's take a look at the electromagnetic spectrum for a moment. So as I said before, electromagnetic spectrum is just a kind of generic term that you use to express all of light. And so here we have a range from gamma rays with wavelengths at 10 to the minus 16th roughly, up to radio type waves, which can go up to 10 to the 6th. And we see, so it goes, smallest is gamma rays, then X-rays, ultraviolet, then visible. That's the range we were working on in the lab where you can actually see it with your eyes. And that's the blue, green, yellow, orange, red. Then infrared, then microwaves, and then finally radio waves. So as we get to those longer wavelengths, remember we said longer wavelength, less energy. That's that 1 over relationship. Energy equals 1 over the wavelength. So the lowest energy will be those radio waves. The highest energy are the gamma rays. By contrast, we know that increasing frequency increases energy. We know that from those relationships we just talked about. And so the gamma rays, the one all the way to the left, that'll be the highest frequency and the highest energy. And then the frequency goes down as you go towards the longer wavelengths, and the energy goes down as well. Okay, gamma rays, highest energy, a lot of that's produced by nuclear transformations. X-rays, that's produced by ionization reactions. So X-ray machines, the kind of things you'd use, like if you went to the doctor, if you broke your arm or something and they wanted to do it, we see that's a pretty high energy light source. UV, UVA, UVB, UVC, the ozone layer protects us from the UV light. That's why you hear all the discussion about concerns about the ozone layer, because it prevents the UV light from hitting us and causing problems. Visible, that's the light that we see, that's the colors that we see, things like that. Infrared is the next. The one I always like about infrared is most of the remote controls are based on infrared. And so that's how you're able to change your channels. Microwaves, of course, heating your food up, and then radio waves, getting FM or AM, depending upon the frequency that it's at. Okay, just to reiterate again, these are the wavelengths going from shortest to longest. And then of course the speed of light. I don't expect you to remember the speed of light. If you need that for a calculation or something, I'll give you that on the tester quiz. The key thing here though is remember that all of this light, no matter the wavelength, is the same speed. Because the speed of light is the speed of light. It doesn't matter which light it is. When we talk about electromagnetic radiation, there's some typical ways we express it. And the ones I want to highlight here are, if you look at for type of radiation, UV or visible, and that's typically in nanometers. And remember, a nanometer is 10 to the minus 9th meters. So if you're doing UV vis and you think about the lab that we did, which was a visible spectrophotometric lab, that was nanometers, right? When you were setting your spectrophotometer, you set it to 400 nanometers or whatever the number was, but that was nanometers. That is usually what people work in when they talk about UV and visible light as nanometers. Micrometers is commonly used in infrared. And so that's another one that you see in chemistry a lot. The others, to be honest, aren't used that often in chemistry. There are other applications, but definitely you should know nanometers for UV and visible is the units that you're going to see in chemistry. And there's a good chance you'll see micrometers for infrared. Okay, so we talked a little bit about waves and what that means in terms of wavelengths and frequencies and things like that. What was found, though, is that while the wave properties of light explained a lot of stuff, it didn't explain everything. And there were three key exceptions that were noted. And they needed to figure out, well, how do we explain these things that we're observing with light, associated with light? Because it's not clear how that relates to the waves. The first is emission of light from hot objects. That's called black body radiation. So if you think about it, you know, if you've ever seen like a piece of metal that you heat up, it glows. Or if you have like coals in a fire, they glow. So you're adding energy into it. And so the object is heating up, but it doesn't just burn up, it emits light. So what's going on with that? And like I said, that's called black body radiation. Then the next one was emission of electrons from metal surfaces on which light is shown. And this is called the photoelectric effect. So it was noticed, excuse me, it was noticed that if you put the right kind of light on a piece of metal surface, and the surface has got to be clean, but if you do that, then the metal will actually emit electrons. And that's the photoelectric effect. So what is causing that? What does that mean? How do you explain that? And then finally, the third one was emission of light from electronically excited gas atoms. And this is called emission spectra. And so what has been found is that if you get enough energy into certain gas atoms, they will emit light at specific wavelengths. And so how do you explain that? So these three observations, black body radiation, photoelectric effect, and emission spectra, led them to think, okay, the wave idea, the wave theory doesn't explain everything. So there must be something else to this. So Planck proposed that energy is released or absorbed by atoms only in discrete, what he said, chunks. And so those chunks of energy became known as quanta. If you just have one, it's quantum. So you're here later on, we'll talk about something called quantum mechanics. That's where some of this terminology comes from. So these chunks of energy, that, as Planck called it, were unique to things, to atoms. And so there's a relationship where energy equals Planck's constant, the 6.626 times 10 to the minus 34th rather, joules second. So that's not joules minus second, it's joules second. So joules times second, think of it that way, times the frequency. So this told us that these definite chunks, these quanta of energy, are the key to understanding this. And so matter can only emit or absorb energy in multiples of this Planck's constant times the frequency. So it can be the constant times 1 times the frequency, the constant times 2 times the frequency, 3, etc. But it can't be 1.2 or 3.2 or something like that. It has to be in these quanta. Because energy can be released only in specific amounts, the allowable energies are what they call quantized. So when we see things going on, we don't see these discrete chunks, so to speak. But on the atomic molecular scale, that's what's going on. And that's why you can do certain things and you don't get a response, and you do other things and you do get a response. Because if it's not that right, it's almost like You got to have the exact right amount of energy to make something happen. If it's not that amount, then it doesn't happen. And that's what they're really getting at here. So let's take a look at how they figured this out with these. So the photoelectric effect, that was the one that we talked about, where if you shine light on a metal surface, you can get electrons emitted. And what was found is that there's a minimum frequency of light that's needed, and it varies from metal to metal. So if you, in other words, if you don't have the right frequency of light and you shine it on the metal, you don't see the electrons being emitted. If it is the right frequency, so in other words, if it's the right quanta, the right chunk, then you'll get electrons emitted. So the energy that's striking the metal behaves as kind of like a series of little energy packets, or a stream of energy packets. And these are called photons. Each one of those is a photon. So you may have heard of the term photon before. This is where it comes from. So those photons hit, if they're at the right energy, so in other words, if they're at the right frequency, then it causes the transition, and then you get the electrons emitted from the metal. So a certain amount of energy, called the work function, is needed for the electrons to overcome the attractive forces holding them in the metal. So there's attractive forces in the metal that keep the electrons with the atoms. You got to get the right amount of energy in there to overcome that attractive energy, which then allows the electrons to be released. If it's not enough, if the energy packet isn't the right value, then it doesn't release it. You've got to have the right amount of energy. Just in increasing the intensity of the energy doesn't do it. It's got to be the right frequency. So if it's the wrong frequency, it doesn't matter how much energy you put into it, it's not going to release the electrons. It's got to be the right frequency. And so once again, there's that formula, energy equals Planck's constant times the frequency. And this is why we're saying is that for there's discrete energy levels for these transitions to occur. And so in order to meet that criteria for the discrete energy level, we see Planck's constant doesn't change. So the only thing that we got to work with is the frequency. So you got to tune it into the right frequency. Okay, let's talk about atomic emissions for a moment. So here we have examples of neon on the left, that's the kind of reddish orange one, and then hydrogen on the right, and that's the purple one. So it was observed that if you put energy into this, then you would get these colors coming out of these gases. And it was like, what's going on with that? So there's two types of spectra. There's continuous and there's line. Continuous would be like the light bulbs. That's a range of wavelengths that's putting out, and you kind of see the result of it all together. Now you can prove that by putting a prism in front of a light. Like a lot of times you'll see light coming through the window, and the window acts as a prism, and you see all the different colors, the visible colors. That tells you that that light source really is a continuous light source, that all those wavelengths are there, and there's a way you can separate the light. The other one is a line spectrum, and there's an example of that here on the bottom, where you see for hydrogen and neon, you see hydrogen, there's 4 colored lines. There's one around 400, a little below 450, around 500, 650. Neon has more of them, but there's discrete lines. So in other words, if you look at that and did the prism experiment like they're doing on the top, you wouldn't see the continuous, all the colors going together. You would just see these particular lines, these particular wavelengths. And so every element has a unique line spectrum. So in other words, every element has a unique emission pattern of wavelengths that they will emit light at based on the energy that goes in. And there's actually a discipline in analytical chemistry known as atomic spectroscopy, which leverages this knowledge about what wavelengths different atoms emit at, and then you monitor those particular wavelengths to determine how much of that is there. So that's a way that a lot of people do trace metal analysis. So if we focus on the hydrogen spectrum, that's the one that has the 4 lines. Rydberg, Balmer, and Bohr came up with some math to explain what's going on there. And one of the things here is this RH that's a Rydberg constant, which we're not going to go into, but they'll give us the value here in a moment. Bohr adopted Planck's assumption and explained it in a certain way. And so if we take a look, and so here we're focusing on hydrogen, and when you look at these energy diagrams like this, there's a couple things I want to point out. Is down at the bottom where it says n equals 1, that's considered the ground state. When we say ground state, we're talking about the atom or molecule. We haven't done anything to it. We haven't put any light into it, haven't put any energy into it. It's just sitting there. And how does it like to be under normal conditions? That's the ground state. If we put the right amount of energy, so in other words, the photon has the right frequency, then that will cause a shift. And so either photons are absorbed or they're emitted, but it's discrete energy packets. And so that's where you see n equals 2, n equals 3, n equals 4 on down the line. Those are the discrete energy levels that particular atom or molecule can move to. So if the energy going in matches what that difference is, that energy difference is, it'll absorb it. Once it absorbs and goes to that excited state, things don't like to stay excited forever. So if you don't keep putting energy in, it'll relax back down to its ground state. Then it'll give off that same energy that it absorbed. And so there's discrete levels is what they say. And depending upon the energy that you put in, it tells you which of these states you go to. And so, but it's got to be the exact right amount. You can't put the wrong amount in or it doesn't go to those levels. And so that goes back to, we talked about the photons and discrete energy levels and all that kind of stuff. So these kind of cartoon type things, that drawings that they do where they show the energy levels and going up and the transitions and stuff, that's real key to understanding how these energy sources interact with the atoms and molecules. Okay, just talking about this a little bit more. An electron is in a permitted orbit is in an allowed energy state. An electron in an allowed energy state does not radiate energy and therefore does not spiral into the nucleus. So if it's an allowed energy state, everything's fine. Energy is, as I said, is emitted or absorbed by the electron only as it changes from one energy state to another. This is either absorbed or emitted based on that E equals H times the frequency. So in other words, once again, you got to get the right energy in. Remember we said energy and frequency are directly proportional. So when we say it's the right frequency, we're talking about having the right energy going in. So if the energy matches, and so like in this case, it's going from, I don't know, maybe about minus 218 to minus 75. So whatever that difference is, that's the energy, that's the frequency that you need to be putting in there. So as I said, energy at the lowest state is the ground state. That's the bottom line on this. Energy at an excited state, N is 2 or more. N is what we call the principal quantum number. Since each orbit has a specific value compared to RH, remember, is that constant, that Rydberg constant. transitions from one energy level to another can be calculated. And so that minus 2.18 times 10 to the minus 18, that's that Reinberg constant. Like I said, you don't need to know that. You'd be given that in a question. And then we have the states, the final minus the initial, that inverse, that 1 over value there. So what do values mean when we talk about the Bohr model? Well, a positive delta E means energy is absorbed. So that means a photon is absorbed in this instance. And this happens if the final value is greater than the initial value. A negative delta E means energy is released. So the photon emitted a photon's emitted when energy is released. So the other thing is the energy of the photon must equal the energy between the two states. So in this example, if the energy of the photon was, say, minus 50, that would not be the difference between, like I said, 75 and 218. It wouldn't be the right energy. So nothing would happen. If you hit it with that, nothing would happen. It kind of goes back to, we talked about putting the light on the metal and seeing if any electrons are released. If it's not the right frequency, it doesn't matter. Nothing's going to happen. Doesn't matter how intense it is. It's got to be the right frequency. So what the problem with the Bohr model is it only works for one thing, and that's hydrogen. Okay, and so this is a common theme you see in this early chemistry stuff is these guys think they got it all figured out, and it turns out it only worked for the one thing they were studying. And then when they expand it to other things, the theory kind of falls apart. But there's key learnings that you get. So we're going to stop here, and then we'll pick up with what came after the Bohr model on Wednesday. So just to remind everyone, the quiz has been moved up to Wednesday. That's the quiz on chapter 5 will be this Wednesday. So on Wednesday, the first half of the class will continue our chapter 6 lecture. Second half of the class will be the chapter 5 quiz. The other thing I just want to remind you again of is starting this week, labs will be in EAB 110. Good news is you don't need safety glasses or anything like that, so they won't be fogging up on you. And the other thing is no shifts of lab. Everyone comes at the beginning of lab, and we'll have everyone in the room together. So any questions before I sign off? Okay, thank you.